Okay, so next part, 5.6, and we'll talk about what's called first homomorphism theorem. So I learned about first homomorphism theorem when I was about maybe in the 2nd grade at elementary school, and the reason was because my father wanted me to go to sleep, and for that he would tell me some mathematical stories. And to make me sleep faster, he was using various mathematical words which I was not able to understand. And actually in Russian this homomorphism theorem is very beautiful. It says that гомоморфный образ группы изоморфен фактор группе по ядру гомоморфизма, which sounded extremely amazing to me. And I started to repeat these words at school to my classmates, and they didn't like that. So it took me many more years to understand what this theorem actually says, and for this entire time I thought it is something very amazing, some very deep fact about mathematics. It's actually not, it's quite a triviality, so it's super important, very useful, but nothing too surprising given what we already know. So, theorem. So suppose that we have f from G to G prime is a homomorphism. Then image of f, that's a subgroup here, is isomorphic to G factored over the kernel of f. So if you take your group and you have a homomorphism somewhere, its image is just the factor group, and by is I mean isomorphic. So of course it now should seem as almost something trivial, because I remind you where we came up with this construction, because we were taking this G prime, and we looked where different classes go, and you know they go to this kind of Gn goes to f of g, and so this is how we came up with this group at the first place. So that should not be hard to prove, and indeed the proof is very formal and relatively trivial. Let me do it, because there will be more proofs like that in homework and later on, so it's classical kind of abstract algebra nonsense. Let me do it for you very carefully. So I want to construct this isomorphism, and for this I need to say where everything goes, and I will do G over kernel of f to image of f. So construction. And so I will denote this homomorphism let's see. Okay, anyways, let me denote it by H. So I want to construct a homomorphism from G factored over the kernel of f, which I will denote by H, to the image of f. And what do I do? So I need to take H and apply it to a class of some element. And of course I know this class is this one, so I have to send it to f of g. And this is f of g. That's a definition. And then of course the question is again correctness, that is a homomorphism, and that is an isomorphism. So correctness. So if I take another element, if g prime equals to g double prime, then there exists some element n in the kernel such that g prime equals to g double prime n. And then we know that this means that f of g prime will equal to f of g double prime n, open brackets, that's f of g double prime f of n, which is f of g double prime. Everything is very obvious. So it means two classes are the same, elements are the same, so h of g prime equals h of g double prime. So correctness is very simple, and it's actually the hardest. Everything else is even simpler, because if you now take h of g1, g2 class, that's of course f of g1, g2, and this is f of g1, f of g2, and this is h of class g1 times h of class g2. So nothing to worry about. So finally, why it is bijective? So surjection is obvious. I mean, just think about it. You have any element in the image is f of g. So any element here is f of g. So it's the image of the class of g. And injective. Remember, so if you need to check some homomorphism is injective, you just look at the kernel of it. And I don't want to write down the word kernel. There will be too many of them. But let's just look what can go to identity. So h of g is identity. Of course, it means that f of g is identity. So g is in the kernel of f. So the class of g is identity in the factor group, g over kernel. So that's it. That's the end of the proof. So bijective homomorphism exists, well defined. That's done. And all examples from previous class give you that. In particular, for instance, maybe one example was a little bit strange. So when I said we have this S3, S4 mapped to S3 surjectively, and then S3 is the image, so S3 is isomorphic to S4 factored over V. So how you can think about this map? You can say this fact. You can think that if you have a homomorphism, you know the image. So to know the image, you just need to know the kernel, and then you just do factor group. Of course, you cannot know G prime in general, because it might happen that you first do this map to G over kernel, to the image, and then you make some injective map somewhere else, and you will never detect it by just looking at G. But detecting the image you can, and this is just this factor group. Okay, so hopefully this is not too much, because now let me do one slight twist. I want to give you a slightly more abstract, basically, version of the theorem, which is called a universal property of a factor group. Okay, so universal property. So actually, that's not something I necessarily need to discuss right now, and not that I'm going to use it that much. So this starts to be kind of a discussion which will continue next quarter, this kind of abstract algebra language. And I want to give a first example of a universal property in algebra, which means that you are trying to describe something or explain a property of this construction, which is not by explicitly saying what it does, not by defining it explicitly, but to saying how it behaves socially. By social behavior, I mean with respect to other groups, other homomorphisms. So let me formulate it, and then we will see why. It's an obvious statement, but maybe it takes a little bit of time to understand why I even want to talk about it. So, this universal property says the following. So assume we have a homomorphism from G to G prime which I will denote by F, and N is a certain normal subgroup in G contained in the kernel. So two conditions here. It's normal in G, contained in the kernel as a subgroup. So then there exists a unique map from G factored over N to G prime, which I will denote by F bar, such that and then let me say this magical word you will hear many more times in math. The following diagram is commutative. Okay, so first let me draw a diagram. So you have G, you have a map G prime, you have a map to G over N, you have a map to G prime. This is F, this is F bar, this is projection P. Okay, what that means. So first, let me explain again the language. So we have a group, G is mapped to G prime, N is some subgroup of the kernel, normal in G. That should be fine. So, and then the statement is that we have a map from this factor group to G prime, so that the diagram is commutative, and that means that if you take any element and use arrows as kind of passes, then you will get to the same direction if you follow arrows. So commutative means for every element G in G, we have, if you do F and apply to G, that's the same thing as to apply F bar to P of G. So in other way, F equals to F bar composed with P, and it's so much simpler to think that, okay, we start here, we go here, here, that's the same as here. Usually we'll write this little circle saying the diagram is commutative. Okay, so I know it's a lot to take because you might think, why on earth I'm bothering with all that? But let me firstly I will explain a proof. A proof is just one line. It's obvious thing. And there are two reasons why people doing algebra like this kind of statements. So first reason is something you might understand right now. So let me try to start with it. So the fact is that we have a lot of familiar groups. And if you have a group which you are very familiar with, like matrices or something like that, okay, subgroup of a group is also something you are very familiar with. So normal subgroup is something you can, these are some elements satisfying certain properties, that's fine. Thinking about factor group is harder, just because, this is more abstract thing, right? Some conjugates, some classes, some cosets, something slightly more abstract. So this theorem tells you how to construct maps from G over N to G prime. So where G prime is any group. So it basically tells you that, okay, if you have this mysterious factor group, this is how you construct homomorphism from it. This is how you study it. So that's one reason. Another reason why people like these statements is because actually it uses much less concreteness. You can even prove that factor groups, it's also called quotient group, by the way, it's the only group satisfying this whole property. And this is remarkable because it tells you how to define this without even knowing these details, cosets and so on, kind of more abstractly. And later on, what you'll see is that though we will talk about different other algebraic objects like modules instead of groups or rings or and so on, the concrete things we are talking about will change. We will not have normal subgroups, we will have ideals or submodules or something, and all constructions will be slightly different, but general ideas like this one will be exactly the same. So, and there will be universal properties, they will be exactly like that, there will be these quotients, this theorem will be true. So by the way, you can do everything here with linear algebra. You can So you can say that if you have a linear map, there is a way to construct this kernel of a map which you know what it is, and then there is this factor group construction. This is true, and this universal property gives you a hint how to actually define it, gives you a property should satisfy. Okay, so let me explain why the universal property is true, and this is so simple, I don't want to even write it formally down, that's kind of boring. Let me just say, so, and give one example. So let me erase this part. Okay, so let me do an example. So let me take G equal to Z, and then I have my favorite map to Z over 2Z, which just assigns to the number, this is G prime, this is F, and this just sends to your number to its class in Z over 2Z, and goes to the class of N, which is 0 or 1, depending on N is even or odd. So kernel of F is of course just even integers, 2Z. So I need some subgroup of the kernel to make my statement visible. So let's take 6Z. Integers divisible by 6, and that's a subgroup of the kernel of F. So what our theorem tells us is that there exists a unique map. So first I do Z over, so I have this factor group over N, which is 6Z. So I have a map from Z over 6Z, which is my map P. Okay, and then, so the statement is that there exists a unique map, which usually people denote by this dotted arrow, F bar, this is F bar, so that this diagram is commutative. So what this map does, I mean, okay, so if you have this classes here, 0, let me just use it without any brackets, 0, 1, 2, 3, 4, 5, 6, 4, 5, so 0 will go to 0, 2 will go to 0, 4 will go to 0, 1 will go to 1, 3 will go to 1, 5 will go to 1. And the statement is that this is F bar. So there is a homomorphism from Z over 6Z to Z over 2Z, and this homomorphism just assigns to a remainder modulo 6, 0 or 1, depending on whether it's even or odd. And you know, it's kind of obvious that this homomorphism exists because if you take an element in this group, remainder modulo 6, so you know that this element is corresponds to some conjugacy class in Z with respect to 6Z. So you can take as a representative some integer, and then you can apply F to it. And so there is a way to go from here to here, except you might worry that it's not well defined because you can take different pre-images under P. But then if N is in the kernel of F, it means actually that the map is well defined. So if you want to construct this map, you just say, okay, take the corresponding integer with this remainder modulo 6 and take its remainder modulo 2. And that's very easy to see that that's the only way this map can be defined theoretically. So this why this gives an idea how to prove your theorem in general. So if you want to construct this map F bar, you just say take class Gn here. So it comes from an element G. And so you know that what you want to send it to F of G, because that's the only way the diagram will commute. And the question is, okay, this construction has a choice. You can take G or another element in Gn. But since F, for F, N is inside the kernel, F will send Gn all to F of G. So you can say that F of Gn kind of doesn't depend on N, it's just F of G. And so this why this map is well defined. Okay, so if you want to be this algebra geek, please spend 2 hours thinking about this universal property. If not, you can skip it for now. Next quarter we will see more of them. Okay, so plans for the future. Next few lectures I want to talk about abelian groups and actually do a bit of number theory, which we encountered already, but we will see more, and so I want to spend a few lectures doing some number theory. So probably you should expect next few lectures to be kind of simpler, and after that we'll start doing more geometric examples of groups coming from projective geometry and isometries and so on. And later we will talk about actually classifying groups of different sizes and prove harder theorems about groups.